For your future courses, this chapter here is probably the most important. Part of the reason why we introduce linear algebra as something other than as a way or method to solve linear systems is so that we can get to square matrix eigenvalues and eigenvectors. And the applications are far-reaching. That's most of the real reason is here. We're not going to spend too much time on this because this was an introductory course and we didn't want to spend most of the time on solving linear systems and vector spaces in general. But keep in mind, second year linear algebra class, your physics classes, your differential equations classes will all require you to do some work related to matrix diagonalization. We'll talk about determinants at first, because that's going to help us find the eigenvalues of a square matrix. And once we have the eigenvalues, we can talk about the eigenvectors. And then once we have a good idea as to how we can build eigenspaces, then we can talk about which matrices are diagonalizable and which ones aren't. So the applications, very useful when it comes to simplifying some matrix computations. Definitely differential equations and quantum mechanics. That's going to be a huge area where this is going to be useful. In data analysis, you might use eigenvalues and eigenvectors as well to help with feature selection, to try to mitigate something called the curse of dimensionality. When you have too many variables, how do you pick the ones that are going to be useful to understand what's happening in the data set? Eigenvalues and eigenvectors can also play a role, but this isn't something we'll cover in this course. So overall, the idea of diagonalization is to find a basis of Rn, a special basis, and that basis doesn't always exist. Don't get me wrong, like there's always a basis of Rn. We always know at least a standard basis. But we're looking for a special basis of Rn, which will be very well suited to working with multiplication by a given matrix. So that special basis is associated with some matrix A. Now that matrix is going to have eigenvalues and eigenvectors. These will be the values that are special for that matrix. Eigen, or eigen, I'm not sure how to pronounce it, is a German root, and it means something about something being proper, something that applies to something. So an eigenvector or an eigenvalue, these are vectors and values that are proper to the matrix A, specific or special. In French, we call them vecteurs caractéristiques, valeurs caractéristiques as well. So characteristic values, characteristic vectors. At any rate, whenever you found these special values and these special vectors for the matrix, it turns out that multiplying a matrix by the eigenvector will be the same thing as just doing a scalar multiple of the eigenvector. Eigenvectors, eigenvalues are also linked to a very important quantity associated with square matrices, the determinant. And the determinant is also linked to the matrix's invertibility. So a lot of these pieces all come together, even though at first glance it's not clear that what we're talking about here has anything to do with invertibility. Well, we're not going to right away make the link between the determinant and the eigenvectors and eigenvalues explicit. First, we're going to show you how you compute the determinant, and we'll study some of its properties. Now, we've seen some examples of determinants when we were computing the matrix inverse. Like you might remember that we had a 2 by 2 matrix here, A, B, C, D, and when we compute the inverse of a 2 by 2 matrix, we have this quantity that shows up in front of a transform matrix, right? 1 divided by AD minus BC, that sort of weird cross product here of the two entries. And if that value is 0, then we know that the matrix is not invertible. And if it's not 0, then we know that it's invertible because you can actually divide by it. But what is that quantity? Where does it come from? What is the generalization of that quantity for a matrix which isn't 2 by 2? What if you had a 5 by 5 matrix instead? So the idea of the determinant is a way to generalize this notion to general n by n matrix. When your matrix A is 1 by 1, so if it's just a scalar, just a number alone, an array of 1 row and 1 column, the determinant is simply the actual value. So the determinant of 3 is 3. The determinant of minus pi is minus pi. If you have a 2 by 2 matrix, the determinant is that sort of weird cross diagonal product, A times D. So you multiply the entries on the diagonal and you subtract from that the product of the entries on the counter diagonal. AD minus BC. We sometimes call this the cross product as well, but we don't mean the cross product as in the cross product of vectors. We mean the cross product of the entries in the 2 by 2 matrix. Better to just say AD minus BC here so we don't get confused about the terminology. From an algebraic perspective, that determinant is the denominator, as I've said, in the formula for the inverse of A. And so what we know is that the inverse exists if and only if this determinant, this cross multiplication here, is different from 0. Because if it is equal to 0 in the formula, you're dividing by 0, and that doesn't make any sense. Geometrically, the determinant is the area of the parallelogram that has sides defined by the rows of A. So if this is a vector AB, this is the vector CD, and there's like this parallelogram here. The absolute value of this product would be the area here. So then there's a link between the area of a parallelogram and whether the matrix is invertible. Like, what would it mean for the area to be 0? You don't really have a choice, right? You have to have that the two arrows are parallel to one another. Either they're pointing in the same direction or they're pointing in the opposite direction. But that's the only way you can get a parallelogram that has no area. So we do have a sense here for what this might mean. And if indeed, if the rows are parallel, then when you do the cross multiplication, the terms will cancel out and you'll get a 0. So determinant equal to 0 is a special case, a degenerate case. Either the matrix is not invertible or the parallelogram created by the rows is a degenerate one. It's really a straight line or a line segment. When n is equal to 3, there you use a formula that is very similar to that of the cross product. In fact, if you remember when I introduced the cross product of 2, 3 vectors, I put them in sort of a form, and there was a determinant here, right? And we had the determinant of I, J, K, and then we had like A1, A2, A3, and B1, B2, B3. And we had said that this was a shortcut notation for this sort of formula here. So in general, there is a bit of a link between the cross product of vectors and the computation of the determinant. It's a bit of a stretch, but the link isn't completely far-fetched, and perhaps that explains why we do call the cross product in the case A, B, C, D. At any rate, this is your formula. You start with the first entry in the first row, first column, and then you basically ignore everything that is in the same row and same column. So you're left with E, F, H, I. And so you're going to recursively push back the computation of the determinant by saying, well, once you've identified A as your important entry here, first row, first column, then you remove everything else, then you'll have to compute the determinant of what's left, E, F, H, I. But this isn't done. This isn't it. You also have then to move on to the next entry in your first row, which turns out to be a B here. Now, because it's not the first or the third or the fifth entry, you have to have a negative sign. So whenever you have the second, fourth, sixth entry, you'd have to have a negative sign. We'll talk about this again very shortly. So once you've identified that, you'd remove everything which is in the first row, second column, and then you will compute the determinant of what's left. And you're left with D, F, G, and I. And you're not done. You still have to go and find the third entry in the first row. You eliminate anything which is in the first row, third column. You're left with D, E, G, H. D, E, G, H. You multiply by this thing. And now we know how to compute the determinants of 2 by 2 matrices, and this is why the formula is recursive. We use what we know at the previous step to complete the computation. So here you do cross product. And you end up with A times E times I minus F times H minus B. Again, important here, you have to have a minus. D times I, F times G, and finally plus C times D times H minus E times G. So this result here, when you do the computation, it is a real number. It's a scalar. And we call this formula the Laplace or the cofactor expansion along the first row. And the along the first row bit should tell you that there could be different ways to do this. You can do it along the second row, along the third row, along the first column, second column, and third column as well. So there's many different ways to compute the determinant. The nice thing about this is it doesn't matter what row or what column you've picked. If you do your computations properly, you will always get the same result. So the Laplace expansion is invariant on the choice of the row or the column. And that's going to give us a trick as to how to best compute these things. We'll find some row or some column where the computation would be as simple as possible, right? Because if it turns out that B was 0 and C was 0, then when you do your computations here, it doesn't really matter what's going on here and here because they'll be multiplied by 0 anyway. And then you could reduce the amount of work that's required to get the determinant. And we'll talk about this again shortly. In the three-dimensional case, A is invertible once again if the determinant of A is not equal to 0, although here it's not obvious that that should be the case. In the 2 by 2 case, it was obvious because we had the special formula for the 2 by 2 matrix, the invertibility of a 2 by 2 matrix. Here it's not obvious, but we'll see that that's still the case. In fact, in general, if a square by square matrix has a non-zero determinant, it is invertible. And if the determinant is 0, it's not invertible. From a geometrical perspective, if you look at the scalar triple product, U dot V cross W, and that's going to be the volume of the parallelepiped with the sides defined by U, V, W, and the determinant of A then is the scalar triple product of the row vectors of the matrix A.